expressions have to be assigned some interpretation there. And they also have to be transferred to a sensory motor interface where they can be externalized, typically in speech, but as is now known, it seems comparably in sign, and may not be externalized at all. It's internal thought, for example, which is the overwhelming bulk of language use, statistically speaking. So you have some sort of generative procedure that constructs an infinite array of hierarchically structured expressions and is associated with procedures to map them onto the two interfaces. The simplest possible operation that could produce expressions of that kind just takes, it's going to be recursive, of course, will take two objects already formed and construct from them a new object. And in the simplest case, it won't modify the two objects that were put together. Modifying them would require greater computational complexity. So this operation, call it merge, takes two objects, say x and y, and what it forms is just the set xy. Okay, no modification of either x and y. Just as a matter of logic, there are two possible kinds of merge. One takes x and y, which are distinct from one another, and forms the set xy. Notice, of course, that if you iterate this, you do get structured expressions. The hierarchically structured expressions. So it takes two objects already constructed, x and y, which are distinct from one another, and forms the set xy. Let's call that external merge. The other possibility is that the two objects, x and y, are not distinct. Obviously, that's just logic. And if you look at the mode of composition, it turns out that if they're not distinct, one must be included inside the other. So the second possibility is that you merge two objects, x and y, where one of them, say y, is inside the other, say x, and they're only certain, and y must be, of course, something that had already been constructed. I call that internal merge. Well, so far that's just logic. Internal merge, if you think about its properties, yields what's called the copy theory of movement. So, for example, which incidentally is quite well confirmed empirically by now, that is, it's confirmed at the semantic level. It's obviously false at the sensory motor level. So, for example, if you take the hierarchical expression that corresponds to you saw what, and you apply internal merge, you merge what to the whole thing, what you get is what, and then the set containing what, and the set constructed from you saw what, which happens to be the right interpretation at the semantic level. So the word what is doubly interpreted in a way. It's interpreted in the position where you hear it as a kind of a scopal element, and it's interpreted in its initial position where it's not pronounced, and it's there given the same interpretation as the corresponding sentence, you saw the book or something, as the object of C with all of its properties. So the result of internal merge in the simplest possible form does give the right interpretation at the semantic interface. And as I say, there's plenty of evidence for that and lots of complications and big literature about it by now. But it seems to be fundamentally right. On the other hand, at the sensory motor side, it's radically wrong. So we don't say what you saw what. Actually, it's not totally wrong. There are cases where a residue of what's moved does remain. Typically, maybe only in cases where there's some phonetic requirement that something be there, what Howard Lasnik called the, I keep forgetting what you called it, stranded affix filter. Yeah, if there's some piece of phonetic material that's just got to be attached to something, then the smallest possible residue of what was moved does remain. And some languages, the whole thing remains. So Chinese, you just say you saw what. But interpreting it with the same dual interpretation. But anyway, radically at the phonetic side, it's wrong. The only thing that remains is the thing that was moved. What did you see? Not what did you see what? Well, that consequence follows from pretty elementary computational considerations. If you were to pronounce all of the, notice this is an artificially simple example. If you take any real example, you find copies all over the place. In fact, even in this case, there's internal copies. But if you were to pronounce all of those copies, there would be a tremendous computational burden. Remember that the mapping to the sensory-motor interface includes all of phonology, all of morphology, and probably even the process of linearization. This is contested, but I think it's increasingly plausible that it's true. And that's quite a computational burden. These are the areas of language that are highly diverse, very complex, affected by historical accident, so, like the Norman Conquest and so on and so forth. But whatever we think about it, that's a huge computational burden. And language seems to universally solve the problem by reducing the computational burden, but of course increasing parsing difficulty, perceptual difficulty. Anyone who's worked on parsing programs knows that one of their basic problems is to try to find what are called the gaps. You hear a what at the beginning of the sentence, you got to figure out where it is, which is a huge parsing problem. So you could say, metaphorically, that the design of language faces two inconsistent desiderata. One, to make the use of language simple, and the other, to make the design simple. And universally, it chooses to make the design simple. There's quite a lot of evidence like this, that language structure is optimized for the thought systems, for the semantic interface, at the cost of considerable complexity, often at the sensory-motor interface, meaning in particular for externalization. And notice that one aspect of externalization is communication. There's a kind of a dogma that language is designed for communication or evolved for communication, whatever those phrases are supposed to mean, and maybe nothing. But the dogma, to the extent that you can make any sense of it, seems radically false. It looks as if externalization altogether and communication in particular are ancillary processes, probably both in the design of language and probably also its evolution. Issues that are well worth pursuing. There's a lot of things to say about them, but I'll put them aside. Just just leave it at that. In any event, we seem to have optimization or hope for optimization, something like the SMT at the semantic side, but nothing remotely like it at the sensory-motor side. In fact, the operations that map syntactic semantic structures onto the sensory-motor face violate every computational principle you can think of. Maybe they do the best that can be done with a hard computational problem, namely relating two systems that have nothing to do with one another. The sensory-motor system could have been around for hundreds of thousands of years before language ever emerged, and there's some, but not much evidence for co-adaptation. So whenever language emerged, you get this thought system, and somewhere down the line it gets externalized, but that's a really hard problem. And it's solved in a lot of different ways, and as I said, it's subjected to plenty of historical accident and so on, as we know. But it looks ancillary, secondary property. Well, notice that internal merge is automatically available. If you take the simplest possible computational procedure, you just get internal merge without postulating it. That's another way of saying that is that a simple form of transformational grammar, this is a simplified version of transformational grammar, is just the optimal system. If you don't have it, you'd have to have an argument as to why you don't. There'd be an empirical burden of proof to show that you don't have it. That's not the way things have been looked at for the last, say, if you go back 50 years, it was assumed, that, or even back to the late 40s when I started working on this, it was assumed that some sort of phrase structure grammar's got to be there. And then the question is, do you need other devices? So if my own work in the late 40s involved discontinuous features to try to account for long-distance dependencies, something like kind of vowel harmony carried over to the syntactic domain. By the 1950s, it looked as if transformations, things which take a piece of a structure and put it somewhere else, could be the best way of doing that. But it was assumed at the time, by me too, that phrase structure grammar is sort of given, and the question is, what other devices do you need, if any? Well, it looks as if the opposite is true, that transformations are given, and you don't need phrase structure grammar. By the 1960s, it had already was beginning to be shown that phrase structure grammar is extremely complex, has a lot of stipulations and a lot of complexity. And it was shown by the 60s pretty convincingly, I think, that most of this was unnecessary and you actually could do better without it. And by now, the residues of phrase structure grammar that remain are very thin. Nothing more than merge and some sort of algorithm, maybe a universal algorithm, which again has interesting computational efficiency properties that tells you what kind of an object you form, period. It doesn't even have to be part of the grammar. It could be a third factor property. So phrase structure grammar seems to have disappeared, but at least I think so. But throughout all this period, no matter how much one tried, transformations seemed extremely resilient. It seemed to be very hard to get rid of them sensibly. And I think now we have an understanding of why that's true. Transformations are just there free. If you have to have a stipulation to bar them. If there's some theory of language that doesn't use transformations, it has a double empirical burden to bear. One, it has to give empirical evidence to justify the stipulation that you don't have internal merge, since it comes free. And secondly, you need to meet the empirical burden of showing that whatever other devices are proposed do exist. Okay, so there's a double empirical burden if you don't assume transformations in the simple form given by internal merge. And personally, I don't think there's any way to meet those two empirical burdens. But anyway, that's sort of the logic of the problem. If you can't meet them, it's important for biolinguistics. If there are two kinds of merge, and if they really are used, there's no stipulation, there's no extra complexity in the system that says don't use one of them. So the ones that are automatically available are just used. If that's true, you'd kind of expect in a well-designed system that the two kinds of merge have different interface properties. They work differently at the interface. Well, at the sensory motor interface, it's kind of obvious. Internal merge yields the ubiquitous linguistic property of loosely called displacement. You pronounce something in one position, but you interpret it both there and somewhere else, like, what did you see? So it has an obvious sensory motor consequence. At the semantic interface, it seems, there's an interesting thesis, plenty of evidence for it, not certain. I know there are people here who've tried to deny it irrationally, in my opinion. The theory won't mention any names, but it seems to correspond with what's sometimes called the duality of semantics. There just seem to be fundamentally two different aspects to semantics. One is what you get in artificial systems, invented systems, argument structure. So, agent, patient, goal, and so on. That's one aspect of semantics. The other aspect of semantics seems to be everything else, like information that's used for discourse interpretation, like distinguishing new information from old information, or identifying the type of. Just as a matter of logic, there are two possible kinds of merge. One takes x and y, which are distinct from one another, and forms the set xy. Notice, of course, that if you iterate this, you do get structured expressions. The hierarchical expressions have to be assigned some interpretation there, and they also have to be transferred to a sensory motor interface where they can be externalized, typically in speech, but as is now known, it seems comparably in sign, and may not be externalized at all. It's internal thought, for example, which is the overwhelming bulk of language use, statistically speaking. So you have some sort of generative procedure that constructs an infinite array of hierarchically structured expressions and is associated with procedures to map them onto the two interfaces. Well, modify the two objects that were put together. Modifying them would require greater computational complexity. So this operation, call it merge, takes two objects, say x and y, and what it forms is just the set xy. Okay? No modification of either x and y. The simplest possible operation that could produce expressions of that kind just takes, it's going to be recursive, of course, we'll take two objects already formed and construct from them a new object, and in the simplest case it won't